All right, so today I can reduce radicals by separating perfect squares and non-perfect squares and taking the square root of the perfect squares. So this is building on something that you did back in Algebra 1. You did a little bit in geometry last year. So we're going to start with a couple of the basic examples, and then we're going to kind of move into the more complicated ones. So first off, we need to be familiar with our perfect squares. So perfect squares, we talked about already this year. It's the result you get when you multiply a number by itself. So I'm going to write out my first 10 integers. And then we also said that all even powers for variables, all even powers are perfect squares. So let's just focus on the integers for now. Let's say I have something like radical 12. Well, I can't take the square root of 12 because it's not on my list, so I have to reduce it. So here's the procedure. I'm going to break it down into two radicals. I'm going to write PS over the first radical and PS over the second radical. 12 would fall there. I want to find the largest perfect square that I can divide into 12. 9 doesn't go in, 4 does. So it'll become 4 times 3. That's step 1. Step 2 is to take the square root of the perfect square. The square root of 4 is 2. When I take the square root, the radical goes away. The non-perfect square comes down. And that's my answer. Let's try one more basic example. Radical, let's do 63. It's not on my list, so I need to break it down into perfect squares and non-perfect squares. I'm looking for the largest perfect square that divides into 63. Can't be bigger than 63. 49 doesn't go into 63 evenly. 36 doesn't go into 63 evenly. 25 doesn't go into 63 evenly. 16 doesn't go into 63 evenly. 9 does. 9 is my perfect square. 7 is my non-perfect square. That's step 1. Step 2 is to take the square root of the perfect squares. Square root of 9 is 3. Non-perfect square comes down. So I want you to try number 1. I'm sorry, you know what? Let's skip number 1. Let's jump right to number 2. Or I have something in front. So if I have something in front, I'm going to just ignore it for the time being. Again, it's good to list my perfect squares whenever I'm doing this. So I would just have them written down somewhere on a separate sheet of paper so you can always have them to refer to in this unit. The 2 is going to stay in front. I need to reduce the 90. So I'm looking for my largest perfect square that divides into 90. 81, no, 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 yes. That's step 1. Step 2, take the square root of my perfect square. The square root of 9 is 3. Non-perfect square comes down. And if there's something in front, I'm just going to multiply that by what it's outside. And I end up with 6 rad 10. Number 3, again, I want to break it into perfect squares and non-perfect squares. So I'm writing PS for perfect square and PS for non-perfect square. Again, I keep on writing them out, but it'd be good if you just have them written out in one spot so you can keep on referring to them for each problem. 48 would be here. 36 doesn't go in. 25 doesn't go in. 16 does. 16 times 3 is 48. My 3 stays outside. That's step 1. Step 2, take the square root of the perfect square. The square root of 16 is 4. The non-perfect square comes down, and the 3 in front comes down. I multiply my two outside numbers, and my answer is 12 rad 3. Now I can show you a little trick to help you come up with these values. It's the same trick that I showed you with factoring. Y equals, I got a lot of crazy stuff in there. Y equals 48 divided by x. And you go to your table. So these are all the numbers that multiply to 48. And basically, you're just looking for which number on the perfect square list you see in your Y1 column. 48 is not on the list. 24 is not on the list. 16 is. So you can use this calculator trick to help you. I wouldn't say as honor students you need it, but it may help you. And if it helps you, then go for it. Use it. Number 4. If you didn't have a chance to do number 4 already, I'll pause. Okay, let's take a look at number 4. I'm going to, again, 99 is not on my list, so I'm going to, again, quickly write out my list, although you should just have it written out so you can refer to it. 99, 81 doesn't go in, 64 doesn't, 49 doesn't, 36 doesn't, 16 doesn't, 9 does. My perfect square is 9. My non-perfect square is 11. You don't put the bigger number first. You always put the perfect square first. The number from this list is what always goes first. The negative 2 just comes down front. That's step 1. Step 2, take the square root of the perfect square. Non-perfect square comes down. Negative 2 comes down. Multiply the values that are outside. And that's your answer. All right, so now that we talked about dealing with just integers, we're going to talk about variables. And before we integrate it in, let's kind of take a look at how it works on its own. So we said that all even powers are perfect squares. So if I'm doing radical x to the 8th, x to the 8th is a perfect square because the power is even. It's a multiple of 2. And we already talked about this earlier this year. To take the square root, we divide the power by 2. So the square root of x to the 8th is just x to the 4th. If it's an even power, we just take the square root of it. It is a perfect square. And to take the square root, we divide the power by 2. Now, if it's an odd power, odd powers are not perfect squares. So here's what we have to do. Just like what we just did, we're going to break it down into perfect squares and non-perfect squares. The perfect square, we're going to drop the power down by 1. So x to the 9th isn't a perfect square, so I can drop it down to x to the 8th. That's a perfect square that goes into it. Since there's an x left over, that leftover x is going to go in the non-perfect square. Now, the square root of x to the 8th is x to the 4th, and the non-perfect square x just comes down. So, if I have x to the 6th, y to the 11th. I'm going to break it down into perfect squares and non-perfect squares. Is x to the 6th a perfect square? Yes. It's an even power, so the whole x to the 6th is going to come over here. Is y to the 11th an even power? No. So I'm going to drop it down 1 to y to the 10th. That's my perfect square. And then I have a leftover y to go with the non-perfect square. That's step 1. Step 2, take the square root of the perfect squares. The square root of x to the 6th is x to the 3rd. The square root of y to the 10th is y to the 5th. And the non-perfect square y comes down, and that's your answer. So now we're going to integrate that into what we just did for example number 5. I'm reducing a radical. I want to see my perfect squares. And because I have an integer, an x, and a y, it's kind of like 3 separate problems in one. I'm going to separate into 2 radicals. Now, notice I made bigger radicals this time. I made bigger radicals because I'm going to have multiple things in each radical. And think of it as 3 separate problems. Let's start with the 12. 12 is not on my list. What's the largest perfect square that goes into 12? 4. So 4 is my perfect square. 3 is my non-perfect square. Again, I'm just looking at the 12 right now. I'm ignoring the x to the 4th and the y to the 7th. I'll get to them in a moment. Now that I'm done with the 12, I'm going to look at the x. Is x to the 4th a perfect square? Yes. It's an even power, so the entire x to the 4th goes there. Now that I'm done with the x, I'm going to look at the y. Y to the 7th, is that a perfect square? No. So I drop the power by 1, and I put that leftover y in my non-perfect square radical. Think of it as 3 separate problems, the integer, the x's, and the y. And in the first step, I'm not taking the square root of anything. I'm just separating perfect squares and non-perfect squares. Step 2, I take the square root of my perfect squares. The square root of 4 is 2. The square of x to the 4th is x squared. The square root of y to the 6th is y to the 3rd. My non-perfect square comes down. That's my answer. Number 6, I have something out front here, so I'm just going to ignore that until the very end. So that 3 in front, I'm just going to ignore for now. Perfect squares, non-perfect squares. I'm going to keep the 3 up front. 3 separate problems. The 45, the x to the 3rd, the y to the 5th. I'm going to treat them all separately. So 45, what goes into 45? No, no, no. 9 does. 9 and 5. X to the 3rd. Is x to the 3rd a perfect square? No, it's not a multiple of 2. So I drop it down to x squared, and the extra x goes in the non-perfect square radical. Now I deal with the y's. Y to the 5th, I drop down to y to the 4th. I put the extra y in the non-perfect square radical. That's step 1. Step 2, I take the square root of the perfect squares. The square root of 9 is 3. Square root of x squared is x. Square root of y to the 4th is y squared. 3 comes down. The non-perfect squares are trapped. I multiply what's outside. That's my answer. At this point, you've had an opportunity to try number 7. So I'm going to break this into my perfect square radical and my non-perfect square. I'm going to make them big so I have a lot of room to work. Since I have 3 reducing problems, essentially, I have the integer, the x, and the y. Again, I guess I'm kind of quick at this. You don't need to write it out every time. You should just have it to refer to, written out already. 80, 64 doesn't go in, 49 doesn't, 36 doesn't, 25 doesn't, 16 does. My perfect square is 16. My non-perfect square is 5. X to the 4th is an even power. It's a multiple of 2, so it's a perfect square. There's nothing left over. It's a perfect square. Y to the 5th is not, so I bring down the power by 1, and I have my extra y left over. My 2x squared y just comes down in front. I take the square root of my perfect squares. Square root of 16 is 4. Square root of x to the fourth is x squared because I divide the power by 2. Similarly, the square root of y to the fourth is y squared. My non-perfect squares come down. Then I multiply 8x to the fourth, y to the third, rad 5y.